alternative electricity options sustainable? This week, you have been exploring the answers to these questions related to sustainable electricity. What are alternative electricity options? How do alternative electricity options work? What sustainability implications are associated with alternative electricity options? How can we compare these implications quantitatively through sustainability indicators? And how do alternative electricity options compare with conventional electricity options across sustainability indicators? You have been watching a series of short videos to get a crash course in understanding how these alternative options work. I will not go into detail about how these alternative electricity options work, since the videos speak for themselves and do a nice job of explaining this in an easy to understand way. Much of your time this week has been focused on categorizing the sustainability of 4 alternative electricity options, based on how they compare in terms of economic, environmental, technical, and social sustainability indicators. I encouraged you to keep a chart like this handy while you have been watching videos and doing readings, so you could keep track of different sustainability indicator information for each alternative electricity option you selected across each sustainability category. If you did that, your chart of information might look something like this, except you were only required to keep track of 4 alternative options. There is way too much information here to fit on a slide in an easily readable way, so I have uploaded a spreadsheet to Blackboard so you can look at all of the summary information I have compiled from this week's course materials for all alternative electricity options covered this week. Please study this spreadsheet for your exam, since it includes information on all of the alternative electricity options from this week's course material, not just the 4 you selected for your discussion assignment. Go to the same area where you found this Week 7 recap video, and you can click here to download the spreadsheet. Although you may not have compiled all of this information during your studies this week, you probably noticed that there were some improvements over last week's comparison of the conventional electricity options. Namely, there was a lot more quantitative data about sustainability indicators in each main category of sustainability. And these data were actually comparable across several alternative electricity options, and even across some conventional options. This is mainly due to this article, Sustainability Assessment of Electricity Generation Technologies Using Weighted Multi-Criteria Decision Analysis by Alexandru Maxim. This is one of very few articles that quantitatively compares a wide variety of electricity options across several sustainability indicators in each category of sustainability. This is a very recent article that is currently in press in the Journal of Energy Policy. This article represents an advancement over other articles of similar subject matter because other articles tend to assess only a limited number of technologies or assess several technologies but use a single sustainability dimension, address only 3 dimensions of sustainability, economic, environmental, and social, apply equal preference weights to all sustainability indicators, and do not use life cycle analysis. By contrast, the Maxim article analyzes 14 different electricity generation technologies, addresses 4 sustainability dimensions, adding the technical dimension to economic, environmental, and social, uses a survey to elicit preference weights for sustainability indicators from 62 academics in the fields of energy and environmental science, and uses life cycle analysis wherever possible because it is a very comprehensive analytical method. The Maxim study uses an analysis method called multi-criteria decision analysis, or MCDA, due to its effectiveness in supporting decisions which involve trade-offs between conflicting objectives. This method involves 5 main steps. 1. Select a set of electricity generation technologies. 2. Select and quantify a set of sustainability indicators. 3. Select preference weights for each indicator. 4. Calculate a numeric score for each technology based on each indicator value and weight for each technology. And 5. Use these scores to rank each technology. Maxim presents the 14 electricity generation technologies used in the assessment in Table 1. The technologies include 5 of the 10 alternative energy options we explored in this week's course material, along with the 4 conventional options from last week's course material, and a few others. Maxim selected 10 sustainability indicators, 1 from the economic sustainability category, 3 from the technical sustainability category, 2 from the environmental sustainability category, and 4 from the social sustainability category. I will take a minute to go through each of these indicators over the next several slides. But it is important to note here that by selecting more indicators for one sustainability category, that implies that more importance is put on that sustainability category. For example, since there are 4 social indicators and only 1 economic indicator, more emphasis will be placed on the social value of each option than on the economic value in the final ranking. You need to consider whether you agree with this approach. Levelized cost of electricity, or LCOE, is the only economic sustainability indicator Maxim considers. LCOE is generally used to compare the average production cost, or break-even sale price, of electricity for various generation technologies over their entire life cycle. Maxim uses the Projected Costs of Electricity Generation report published in 2010 by the International Energy Agency and the Nuclear Energy Agency for the LCOE data. This report displays the LCOE for approximately 200 power plants located in 21 countries, which can be classified into various technology types. Maxim estimated a weighted LCOE average using the nameplate capacity of the power plant as a weight. Nameplate capacity refers to the amount of megawatts or gigawatts the power plant can produce at full rated capacity. Weighting the LCOE in the nameplate capacity can generate errors since not all power plants operate at their nameplate capacity during similar time period. For example, baseload generators operate at the nameplate capacity more often than peakers or intermittent renewables, which translates to different maintenance and operating costs among even otherwise identical units. It is important to note that many references report LCOE values that are very different from the ones presented here. In the United States, the best place to look for the full range of LCOE values is the OpenEI Transparent Cost Database. The OpenEI Transparent Cost Database shows the LCOE, overnight capital cost, fixed and variable operating costs in US dollars, estimated by the Department of Energy and others, based on historical data and projections for 19 electricity generating technologies as a box and whisker plot with the minimum, maximum, and median. You can explore the data by year and see the parameters used in the calculations. This chart shows a very different picture than Maxim's LCOE table. For example, Maxim reports the LCOE of solar photovoltaics to be $203 to $304 per megawatt hour, depending on the discount rate. The discount rate basically refers to how much you value getting your money now rather than later. At a discount rate of 7% in between the two discount rates Maxim uses, the OpenEI website shows solar photovoltaics to cost between $150 to $590 per megawatt hour. Similarly, Maxim reports solar thermal to be $178 to $270 per megawatt hour, while the OpenEI database reports concentrated solar power, another name for solar thermal electricity, to be $140 to $460 per megawatt hour. Also, Maxim reports nuclear to be $54 to $87 per megawatt hour, and the OpenEI database shows it to be more in the range of $40 to $540 per megawatt hour. There could be many reasons for these differences, but one of the most likely is that the OpenEI database is based on data specific to the United States, while the Maxim article relies on international data. Also, with respect to nuclear, recently built plants have been more expensive than originally projected. It's possible that the OpenEI database includes these newer, more expensive plants, but the IEA report does not. The first technical sustainability indicator that Maxim examines is the ability to respond to peak demand and therefore to ensure that overall grid stability in the long term in the context of a growing share of intermittent generation from some renewable energy sources. If technologies possess this capability, they can be used for grid balancing, a function that is becoming more important as the share of intermittent generation capacity from solar PV and wind units increases. This is a qualitative indicator, which Maxim turns into a quantitative indicator by assigning a score of 1 to values of yes, rapid, 0.5 to yes, slow, and 0 to no, Intermittent renewables get a no value, and baseload generators get values of yes, although some, like coal and nuclear, are slow to react to changes in demand, while natural gas and hydro can react quickly. The second technical sustainability indicator is efficiency, which Maxim defines as a ratio between the useful energy output and the total energy input, expressed as a percentage. Maxim uses a method for calculating efficiency that compensates for the potential underestimation of renewable energy technologies by evaluating them based on their availability directly as secondary energy sources, rather than considering the conversion from primary energy to secondary. This is why renewables get a value of 100% in Maxim's chart. If you took into account the conversion of vast primary resources like solar and wind into electricity, the efficiencies of these technologies would be more on the order of around 10%. The values for natural gas and coal shown here are for conventional technologies. Clean coal with carbon capture and sequestration would have a lower efficiency than that shown here because the CCS technology depletes some of the energy generated by the power plant. The third technical sustainability indicator Maxim considers is capacity factor, which is a ratio between the actual electricity production of a unit during a certain time period and the maximum theoretical output of the unit if it had been running at full capacity for the entire time period. This indicator shows, on average, how much of the nameplate capacity of a plant is actually used in practice. Using the highest available value, which shows the current maximum potential of the technology. Nuclear, coal, natural gas, geothermal, and biomass are considered baseload generators because they are available most of the time. Hydro and solar thermal could also be considered baseload generators depending on how often they are needed. Wind and solar PV are considered intermittent because they are not available very often. The first environmental sustainability indicator Maxim considers is land use, presented here in square meters per megawatt hour. Maxim considers land use over the entire life cycle of the power plants, the extraction, processing, transportation, and waste disposal of fuels, and the construction, operation, and decommissioning of the power plant. Not many studies have completed this type of assessment, and there is a lot of uncertainty in these numbers. But this comparison shows biomass, large hydro, wind, and geothermal to use the most land, with solar PV, natural gas, nuclear, and small hydro on the low end. The second environmental sustainability indicator Maxim uses is external costs associated with the environment, shown here in euro cents per kilowatt hour. This is a complex aggregated indicator which can be used to evaluate most of the impact that electricity generation has on the environment. It covers an ample array of pollutants and forms of environmental impact, ranging from noise pollution to hazardous emissions, which is listed in more detail in Appendix B, and assesses them over the entire unit life cycle. Examples of factors not taken into consideration by Maxim's study include the visual impact of wind farms, any unique land habitat reduction, and the impact of forced population displacement specific to large hydroelectric projects, as well as biodiversity loss. Costs can be classified as external when they result from the activity of one entity but are incurred by a different entity. One example is the soiling of buildings due to the particulate emissions of a coal plant. The cleanup cost is incurred by the building administrators, not by the plant operator. This is because damages to air quality are not subject to proprietary rights, so a commercial relationship on the issue cannot be established between the two entities. This institutional deficiency can be mitigated through the evaluation of external effects in such a way that the governing authority can internalize the external costs by, for example, imposing taxes on the use of polluting fuels. There were no data for geothermal here, so in the final ranking, Maxim estimated this value to be 0.75 euro cents per kilowatt hour. This chart in Appendix B shows which specific impacts are included in this indicator value. Maxim separated out the impacts related to human health and presents them as a different indicator in the social sustainability category. It is not clear in Maxim's article what values are used for life cycle greenhouse gas emissions related to climate change within this overall indicator. However, the National Renewable Energy Laboratory in the United States has compiled comparative information on life cycle greenhouse gas emissions for each of these technologies. These values are presented as a range because several studies have assessed emissions for several technologies with different results. Although you will often hear people talking about all of these emissions related to building solar panels and wind turbines, as you can see here, and the National Academies conducted a very comprehensive analysis of the external costs related to greenhouse gas and criteria air pollutants in US dollars per kilowatt hour. Here is a summary of their results. There is a range of climate change damages because of the uncertainty associated with the effects of climate change, particularly when these effects will occur and how much we should value effects that happen far into the future. This is a really great study that you should read if you are interested in learning more about this subject. You can go to this website to download a free copy. The first social sustainability indicator that Maxim considers is the impact of electricity generation on human health, which, as mentioned in the previous slide, was evaluated using the same approach as external costs environmental. There were no data for geothermal, so in the final ranking, Maxim estimated this value to be 4.25 euro cents per kilowatt hour. The second social sustainability indicator Maxim considers is job creation, which is a life cycle indicator showing the number of employees involved in the implementation and operation of a power generation project. The measurement unit is called job years, a full-time employee hired over 12 months. Per unit of electricity produced. There is a lot of uncertainty associated with this type of estimation, and a lot can depend on the location of the electricity generating technology. But this chart shows solar PV, hydro, and geothermal as generating the most jobs, and nuclear, natural gas, and coal as generating the least. These values do not show any distinction about where jobs will be created, however. For example, for wind and solar, there may be many manufacturing jobs that occur in one country, while installation jobs will occur in a different country. The third social sustainability indicator is social acceptability, and the results shown here are based on 3 studies, which are shown here with information about the year published, the population surveyed, total respondents, and the questions the respondents had to answer. Maxim then converted these qualitative descriptions into quantitative scores for the final assessment. The high acceptability values for wind and hydro are especially interesting given recent opposition to these electricity options in Maine and throughout the United States. The fourth social sustainability indicator is external supply risk, which is essentially a measure of energy security, which requires that at any given time there is sufficient energy on the market as to satisfy all existing demand at a reasonable price. The external supply risk for biomass is assumed to be 0 because in general the shipment of biomass fuels over large distances is not economically feasible, resulting in a net import dependency. All other renewables do not rely on imported fuels, making the external supply risk also 0, even though there may be reliance on imported manufactured components to build the technology. After selecting and quantifying the sustainability indicators, Maxim conducted a survey of academics from the fields of energy and environmental studies, in which he asked the respondents to rate the 10 sustainability indicators on a scale of 1 to 10 based on their importance for the long-term development of mankind, 1 being not important at all and 10 being very important. He sent the message to 292 email addresses from academics from the energy and the environmental science departments of 6 Romanian universities and received 62 responses. Table 16 was a little difficult to read since it referred to section numbers rather than indicator names and was not sorted by preference. So I created an adapted version, which gives the indicator names and sorts them from most important to least important. The survey showed that the indicators perceived by the respondents to be most important were levelized cost of electricity, efficiency, ability to respond to demand, and external costs related to human health. The indicators perceived to be least important were land use, job creation, and social acceptability. It would be interesting to see how these results vary for United States academics, or for non-academic energy decision makers. Also, think about how you would rank these indicators personally. Using the preference weights and sustainability indicator values from the previous slides resulted in this ranking of electricity options from best to worst. Renewables hydro, wind, and solar PV come out on top, with coal and biomass at the bottom. Are you surprised by this ranking? Is this what you would have expected? Do you agree with it? Large hydro is on top, mainly because it is a free renewable fuel source. It's flexible, it has a low LCOE, and there are synergy opportunities with irrigation and recreation projects. However, it may be surprising that hydro is on top from the U.S. perspective, because most developed economies in Europe and North America have already constructed hydro projects in the locations deemed most technologically feasible and economically viable. Therefore, there is limited undeveloped potential in these regions and increased marginal costs. In addition, the high investment costs could be prohibitive in developing nations, and hydro has faced a negative reputation recently, not even classified as renewable energy sometimes. Maxim states that recent research has repeatedly argued in favor of the responsible development of hydroelectricity as a clean, sustainable energy source, which also indirectly benefits local economies. However, this may not be the best solution for the United States, where new hydro is actually quite a bit more expensive, and where there is not a lot of public support for new hydro. Although there are many strengths to the Maxim article as identified earlier on, there are some limitations as well. I have tried to identify some as I went along, but one that has not come up yet is that Maxim's analysis does not consider comparisons between central generation and distributed generation. It only considers large-scale power plants. But what about solar and wind on houses, businesses, communities? No study so far has compared these options across sustainability indicators in each category. That is something to consider for the future, especially as these distributed generation options continue to grow. It also doesn't consider energy efficiency and conservation. You watch several videos explaining different energy efficiency and conservation options that could be used to help make electricity more sustainable. Although electricity generation options will always be needed, these efficiency and conservation options are just as important. And then there is energy storage. Some see this as the holy grail of sustainable energy, basically solving the biggest problem associated with renewables, intermittency. But no one yet has made energy storage commercial at the right price. The TED Talk you watched, however, highlights one energy storage option that may have that potential in a few years. During this talk, Professor Sadoway expresses that the grid requires energy storage to meet three main demands: uncommonly high power, a long service lifetime, and low cost. And he thinks he has just the technology to meet these demands, although it will take some time for his technology to get to commercial or utility scale. I hope you enjoyed learning about sustainable electricity options. After spring break, we will shift our focus to transportation and heating. But before leaving for spring break, don't forget to take the Unit 2 exam. The exam will consist of 20 multiple choice questions. You are not allowed to communicate with any other person while taking the exam, unless you need to ask me or the TA a question to clarify something. Please review course material before beginning the exam. Make sure to study the weekly recap and introduction videos in particular. You will have 1.5 hours to complete it once you start the exam. During that time, you can log in and out of the website, shut down and restart your computer as necessary, but it will be 1.5 hours total from the moment you begin. The exam will open at 8 a.m. on Wednesday, February 26th, and close at 11:59 p.m. on Saturday, March 1st. At that point, any answers you have saved will be submitted, and if you haven't answered anything, you will receive a 0.